Okay, so this is that last part of this course, right? So now speed control of DC motors, you find things are quite simple. So for example, we know that back EMF is equal to phi z small n upon 60 into P by A. Somewhere I might have used capital N, but same thing, that is why in the bracket it is written small n is equal to capital N. So no confusion. And EB, we know that back EMF EB is equal to your V minus the drop in armature circuit, that is the voltage drop in armature circuit, that is IA into RA, right. For this, it would be seen that the speed of a DC motor can be changed by the following methods. One is by varying the voltage applied to the armature of the motor, that is your V you can vary, that applied voltage. Another thing is by inserting the resistance in the armature circuit to reduce the applied voltage to the armature, thereby changing the armature current, right. And number 3 is by varying the field flux by changing the field current. These are the 3 different ways of changing the your what you call speed of the DC motor. Now, if you look into that, now speed control of a DC shunt motor, right. The most common method of speed control of a DC shunt motor is by controlling its field strength by adjusting the field regulating resistance. If you look into the circuit, that this is your field winding and one additional resistance has been connected, right. This is a variable resistance. If you vary this resistance, then your what you call that your field current will vary. For example, suppose this resistance is RF, right. Suppose this is your RF. So, say RF dash and this field resistance is RF, right. So, when you try to find out what is field current, so IF will be is equal to V upon RF dash plus RF, right. This RF anyway is fixed, it is the field resistance of this circuit of this field winding, and this RF dash actually your what you call that variable resistance. So, if you can vary this resistance, naturally the field current will decrease, right, because you are adding some resistance, field current will decrease. So, in that way your what you call that means your flux is proportional to the field current. So, naturally that your what you call that flux also will decrease, right. But in that case we will see the characteristic how it is. If field current decreases, speed increases. If field current your increases, if field current your increases, then flux also your increases, right. In that case opposite will happen. So, and field that basically IF actually field current phi actually proportional to IF, right. So, this you always keep it in your mind. So, in that case what will happen, we know this, the circuit connections and the relation between flux or phi or IF, this can be phi or this can be IF, because flux is proportional to IF and speed n are shown in figure above. In this method, a variable resistance is connected in series with the shunt field, that is in this diagram, this I showed you, this is the diagram, right. So, the speed is actually inversely proportional to the flux when the applied voltage is not changed and back EMF can be considered constant. That means, this equation this equation, we know this equation, that your EB is equal to that back EMF is equal to, right, your k into your phi into n, right. So, k is the constant and this is the flux, and flux proportional to the your what you call that your field current. So, we know this. So, here it is your what you call, this is the expression, this is that your EB is equal to this expression, right, and if your EB is equal to then k into phi into n, right. So, here it is written that field the speed is inversely proportional to the flux when applied voltage is not changed and back EMF can be considered as constant. That means, your EB back EMF is equal to k into phi into n, right. So, if you applied voltage is constant and EB if you can make constant, then what will happen, that n actually inversely proportional to the your flux, right. So, flux is proportional to IF, that means n is inversely proportional to IF, right. That means, if field current increases, n decreases and vice versa. So, that is why this characteristic it looks like a your what you call this one like a rectangular hyperbola, right. So, this is your n RPM and this is your field current, right. So, this is the characteristic. Now, next is your this increasing the resistance in the shunt field decreases the shunt field current, hence decreases the flux and increases the speed, because inversely proportional to it. In the same way, decreasing the resistance in the shunt field circuit increases the shunt field current, hence increases the flux and decreases the speed, right. This is one method. Another is the armature resistance control method. In this method, resistance actually here it is inserted in series with the armature circuit. This is your R, this is your R, that resistance is inserted here, and armature resistance, I mean it is your RA, small RA, right, and this is the field current, here nothing is there. So, increase the resistance in the armature circuit means then this is your back EMF. So, if you apply in this circuit KVL, you will get EB is equal to V minus IA into R plus RA. RA is the armature resistance, right. So, therefore, increase the resistance in the armature circuit IARA, that your this, if you increase this capital R, right, then drop increases, therefore, EB will decrease, right, and speed of the motor actually decreases, because back EMF, because your in this case your EB back EMF is equal to K into phi into N, right. So, what is happening here, that because we have inserted that resistance R, so this drop will increase, therefore, EB will decrease. So, in that case your field current IF remains constant, because nothing is connected here, because this voltage V remains constant. So, in that case phi is also constant. So, your because of the decrease of EB, N all speed also will decrease, right. So, almost linearly it should vary. So, in this case what will happen, by this method the speed of the motor can only be decreased, you cannot increase it, because of this your EB is decreasing, right, you cannot this thing you can, because you have added R. So, EB is decreasing. So, by this method only speed can be decreased, right. So, this characteristic you can easily draw. Now, second one is that speed control of DC series motor. Now, this is for shunt. So, nothing is there actually, you put a resistance R, capital R, and this, because of that there will be voltage drop and field current remain constant. So, back EMF will decrease, therefore, speed will decrease. So, this method you can only, or what you call, you can only decrease the speed of the machine. Now, next is your speed control of a DC series motor. DC series motor actually field winding we have seen is in series with the armature, but what is this, that you connect one variable resistance we call diverter, that is in parallel to this field winding. So, the way you have studied your simple parallel circuit for DC circuit analysis. So, as soon as you, and this is a variable, as soon as you connect it one, part of the, this is the total armature current I, this is the total current IA, right, and the same current is going here, but part of the current will be flowing through this your I, and part of the current flowing to the field winding, right. That means IF plus IA is equal to capital I suffix A, right, IF plus I is equal to IA. So, by this way part of you are basically you can control this field current by adding a diverter. Diverter means part of the current is diverted to this variable resistance, you can vary this. So, the speed control of a series motor using a diverter. So, this method used for controlling the speed of the series motor is to vary the field flux by varying the your excitation current, because the excitation current means the field current, right. Here the regulating resistance for the purpose is connected in parallel with the field winding. This is known as diverter. By adjusting the diverter resistance, the field current can be regulated by diverting the desired fraction of the main current. So, this is main current. So, part of the current can be flowing through this, such that field current will decrease, right. So, now this is one way. Another way is that as an alternative arrangement, the number of series field turns are varied by employing a tap field control. In this case what happens, this is a series field, this is basically series field, many places tap, it is tap. If you connect this tap, naturally your what you call, this is the path it will follow, that your what you call this your what you call, this is the path it will follow, right. And if you, I have not marked here, it is A1 A2, right, this is plus minus, right, and this is your what you call, by changing this tap from here to here, what to here, you can control the current to the field, right. So, this way also, this is called tap field control, this way also you can control the your what you call that your control the speed of the series motor, right. So, details mathematics other thing just keeping at the first year level. Now, number 3 is that if a resistance is connected, but again series motor in connected in series with the armature circuit, the speed of the motor can be reduced by adjusting the resistance as the back EMF. I mean, here if you put one resistance in series with the field winding, because both are in series, and series this resistance of this armature is Ra, right. So, armature, and this is RAC, right, and this is R. Therefore, back EMF, that EB, the back EMF will be V minus Ia into R plus RAC plus Ra. This RAC is the series field winding resistance here, series field winding resistance. So, in that case we are adding one resistance R, right. So in this case also the speed of the armature can be reduced by R, because if you do so, the back EMF is getting reduced, right. So by the adjusting the resistance of the back EMF, hence the speed will be your what you call reduced by increasing the resistance in the circuit. So if you increase the resistance, so naturally your back EMF will decrease, right. So in that way speed can be reduced, right. So like your armature control in shunt motor. So next is the reversal of rotation of DC motor for shunt motor. Suppose this is the connection of the shunt motor. F1 F2 is the field terminal, A1 A2 armature terminal, right. So if you want to here also it is shown your what you call F1 F2 and this thing. Now if you want to interchange the if you interchange the field terminal, then if you see this diagram, F1 F2 connected, but now this point is connected here and this point is connected here. This is, that means your direction of this is the earlier it was your what you call current was flowing in the field from F1 to F2. This connection is flowing F2 to F1, and torque is proportional to your product of the you have seen that product of your phi into Ia, right, and phi is proportional to your field current, right. So in that case what will happen, as you are your field winding current is reversed, the machine will rotate in the opposite direction. Here it is shown in the clockwise direction. So here it will rotate in the opposite direction if you reverse your only field connection, right, field winding connection. Now if you interchange, now keep the field as it is F1 F2, now interchange the armature connection, right. That means plus terminal here has brought to A2 and minus 1 has brought to A1. I mean here just we have interchanged these two connection A1 and A2 reverse. In that case your what you call direction of the armature current is changed, but field current direction remains same. So machine will rotate in the opposite direction, right. So your that is either, that means either you interchange the field connection or you interchange the armature connection, so that machine will rotate in the reverse direction. But if you interchange both F1 F2 and A1 A2 both, machine will rotate in the same direction, because torque is proportional to the what you call your phi into Ia, right, product of these two, right. So in that case phi is proportional to If, so both If and armature current direction is changed, so machine will rotate in the same direction, right. So that means if you either of these if you interchange, machine will rotate in opposite direction, but if you change both, then machine will rotate your what you call in the your opposite direction. If you both you change, then machine will rotate in the same direction. And another thing is the terminal voltage. If this terminal voltage, suppose this is plus, this is minus, if you interchange this terminal, suppose if I connect it to minus and if I connect it to plus, machine will rotate in the same direction, right. In your laboratory you can verify easily, right, because if you interchange also both the field current and your current armature current, both direction will change. So ultimately torque is proportional to your phi into I, as both your phi into Ia, that means in generally torque is proportional to product of field current and the armature current. So both directions are changing, so machine will rotate in the what you call in the same direction. So if you interchange this polarity also, it will rotate in the same direction. If you interchange both field and armature, it will rotate in the same direction, but either field or armature if you interchange, then it will rotate in the reverse direction, right. So this is very simple thing. So now for series motor, here also that F1 F2 is there, A1 A2 is there, and I is equal to field current. Now for series motor also, if you reverse the direction of this one, this point is connected to F2 and this point to connected to F1, then here field current or armature current to the field winding that flowing F1 to F2. Now if you reverse interchange this, it will move F2 to F1. So this way that your what you call direction of this can be changed. Here it is showing in our what we call clockwise, here direction is showing anti-clockwise, because you are reversing the direction of the field current. Similarly, if you reverse the direction of the armature current also in this case, so there here also if you when you are reversing, then in this case also machine will rotate in the reverse direction, but if you make both, then it will rotate in the same direction. If you interchange the polarity of this supply line also, machine will rotate in the same direction, right. Next is an example. So, a series motor having a resistance of 1 ohm between its terminal drives a fan for which the torque actually is proportional to the square of the speed, that means T proportional to n square, right. At 230 volt it runs at 300 rpm and takes 15 ampere. The speed of the fan is to be raised to 375 rpm sorry, by increasing the voltage. Find the voltage and the current required. This is the problem, right. So, at 230 volt it runs at 300 rpm and takes 15 ampere. The speed of the fan is to be raised to 375 rpm by increasing the voltage. Find the voltage and the current required, right. So, we know that torque actually proportional to phi into Ia. Now, the in series motor phi is equal proportional to Ia. That means, if phi proportional to Ia, then torque proportional to armature current square. Now, also given that torque is proportional to N1 square. If N1 is the initial speed and Ia1 is the initial current, while N2 and Ia2 are speed and current are the new condition of operation of the motor, then we can write, because it is T proportional to N square. So, first case if it is T1, second case torque is T2, say, then it will be T1 upon T2 is equal to Ia1 upon Ia2 whole square, because torque is proportional to Ia square, right, and it is given that torque is proportional to N square. That means, T1 by T2 is equal to Ia1 by Ia2 whole square is equal to N1 upon N2 whole square. This is the equation 3, it is given. Now, it is given N1 is equal to 300 rpm, N2 is equal to 375 rpm and Ia1 is equal to 15 ampere. This is given, from which from these two equations you can find out Ia2 will be 18.75 ampere, right. Therefore, the back EMF EB1 will be 230 minus first case current was 15. So, 15 into 1. So, 215 volt, right, and N1 is 300 ampere and RAC plus RA we assume 1 ohm, right, total. And next is your, in the second case Ia2 is 18.75 ampere and RAC plus RA is 1 ohm, it is given, this is RAC and this is N2 is 375 rpm. Therefore, EB2 is equal to V minus your 18.75 into that RA plus RAC 1, that is. So, you will get V minus 18.75, but V we have to determine, and we know that back EMF proportional to flux into speed. Therefore, EB1 upon EB2 first condition and second condition you can write phi 1 N1 upon phi 2 N2, right, is equal to, and because you can write Ia1 N1 upon Ia2 N2, because your flux is proportional to the armature current in series motor. Therefore, phi 1 by phi 2 is equal to basically Ia1 upon I2. So, substitute here, it will be Ia1 N1 upon Ia2 N2. So, substitute all these values, because all these values are known, right. So, and this is EB1 upon EB2, EB1 is 215 volt and EB2 is this much, V minus 18.75. So, this one is equal to this one. So, from which if you solve, you will get V is equal to 350.65 volt, right. Now, next is another example. So, this is the answer. So, simple problem, just you have to keep few relationship in your fingertips. So, everything will be solved, right. Now, next is a series motor with negligible field resistance when run at a certain load takes 40 ampere at 500 volt. If the load torque varies as the cube of the speed, the torque is proportional to n cube. Find the resistance necessary to reduce the speed to 80% of its original value, right. So, if initially it was n, it will be 0.8 n then, right. So, you have to find out that what you call the resistance necessary, right. So, for series motor torque we know proportional to armature current square and it is given T proportional to n cube. That means, we can write T1 by T2 is equal to I1 upon I2 whole square is equal to N1 upon N2 whole cube, right, first case, second case, right. Now IA1 is given 40 ampere, V is equal to 500 volt, and N1 by N2 it is given 80%. So it will be your what you call that second case, the speed is 80% of the first case, because we are reducing the speed. So N1 upon N2 will be 1 upon 0.8. I mean it is something like this. If first case is if it is N, first case if it is N, then second case it is 0.8 N. Therefore N upon 0.8 N is equal to 1 upon 0.8, that is written here, right. So that means these are the data given. So 40 square upon IA2 square is equal to 1 upon 0.8 cube, from which we get IA2 is equal to 28.62 ampere, right. Now also we know EB1 is 500 volt, first case given. Second case, some resistance R is inserted. So 500 minus IA2 into R is equal to same as before, phi 1 N1 upon phi 2 N2 is equal to IA1 N1 upon IA2 N2, same as before, is equal to 40 into 1, right. I mean IA1 is 40, IA2 is 28.65. So 40 upon 28.62 into N1 upon N2, actually 1 upon 0.8, right. So from which if you solve, you will get R is equal to 7.47 ohm, right. So this is the answer. This much resistance has to be inserted, right. So next is a 250 volt shunt motor has Ra is equal to 0.5 ohm and RF field resistance 250 ohm. When driving a load, the torque of which is constant, torque is given constant, takes 30 ampere and runs at 500 rpm. It is desired to raise the speed of the motor to 750 rpm. So 500 to 750, you have to raise the speed. What resistance should be inserted in the shunt field circuit, right. So initially there was no resistance in the circuit. So Ra is 0.5, Rf 250, I1 30 ampere, N1 500 rpm, right. So everything is given. So given that the torque of the load is constant, so torque is a constant, and back EMF in the first case EB1 will be V minus I1 Ra. So V 250, I1 30 and Ra 0.5. So 235 volt, right, in the first case. Now in the second case, we have to raise the speed to 750 rpm. So a resistance R has been inserted here. We have to find out what is the R. While running at 750 rpm, let the current to the armature be Ia2. At that time it is Ia2, right. So that means EB2 is equal to V minus Ia2 into Ra. So Ra is 0.5 ohm. Therefore EB2 is equal to 250 minus 0.5 Ia2, right. This is the circuit diagram for the second case. Now we know that back EMF is proportional to phi into N, or which same as before, we can write EB1 upon EB2 is equal to phi 1 N1 upon phi 2 N2, right. So if and N1 is 500 rpm first case and N2 is the 750. So 500 upon 750 into phi 1 by phi 2, that is 2 phi 1 upon 3 phi 2. This is equation 3, right. Now torque is given that proportional to phi into Ia, but torque remain constant. But torque, both the cases torque remain constant. So T1 is equal to T2. That means for phi 1 into Ia1 is equal to phi 2 into Ia2, because this torque remain constant. Therefore first case if it is phi 1 I1, second case it is phi 2 Ia2, from which we get phi 1 upon phi 2 is equal to Ia2 upon I1 is equal to Ia2 upon 30, because Ia1 is equal to 30 ampere, right. Therefore from equation 1, 2, 3, 4, right. So actually this is your what you call this one will be italic, right. This one actually it is actually equation 1, this is your equation 2, this is equation 3 and this is equation 4, actually this way some correction, right. So if you from equation 1, 2 and 3, 4 you substitute all these things, so you will get your what you call that your 235 upon 250 minus 0.5 Ia2 is equal to 2/3 into Ia2 by 30. So if you solve this quadratic equation, one solution may not be feasible and answer will be Ia2 is equal to 46 ampere, right. So little bit practice is necessary. So now from figure A, so as from figure A we get If1 is equal to 250 upon 51 ampere, because if you look into this figure, this is your 250 volt and this is 250. So for first case field current was 1 ampere, 250 upon 250, and in the second case circuit, the figure A, the field current IF1 will be 250 upon 251 ampere, but second case IF2 will be 250 upon R plus RF. So, 250 upon R plus 250 ampere. Now, equation 4, so phi 1 IA1 is equal to phi 2 IA2. So, we know that flux is proportional to the field current. So, we can make phi 1 upon phi 2 is equal to IF1 upon IF2 is equal to your IA2 upon IA1. Substitute IA2 is 46, we got IA1 30. So, 1 upon IF2 is equal to 46 upon 30, but IF2 is equal to 250 upon R plus 250, right. So, is equal to this 46 by 30. So, it will be 30 by 46. So, after solving this for R, you will get R is equal to 134 ohm. This is your answer, right. So, next is that example 6. A 6 pole lap connected 230 volt shunt motor has 410 armature conductors. It takes 41 ampere on full load. The flux per pole is 0.05 Weber. Given that Ra is equal to 0.1 ohm. Field resistance Rf 230 ohm and contact drop per brush is given 1 volt. So, 2 brushes will be there. So, generally it will be total will be 2 volt, right. It is given per brush. Determine the speed of the motor at full load. So, it is given lap connected pole P is equal to 6. So, therefore, for lap connection parallel path will be A is equal to P is equal to 6, right. So, Z is equal to given 410, the number of conductors, that this current IL is given 41 ampere, flux is given 0.05 Weber, Ra armature resistance given 0.1 ohm, terminal voltage V is given 230 volt, Rf is given 230 ohm. Therefore, all this everything is put here and there are 2 brushes. So, delta E will be 1 into 2, so 2 volt, right. So, what will happen? First you find the field current. IF is equal to, look at the cursor, V upon Rf, that is 230 upon 230 is equal to 1 ampere, right. Now, armature current, this IA, at this point you apply KCL. So, IA will be IL minus IF, so 41 minus 1, so 40 ampere. Now, in this case the brush contact drop is given per brush 1 volt. So, EB we know V minus IA, but keep it in your mind also this drop has to be subtracted minus delta E you make, right, such that there should not be any small error. So, but delta E will be 2 volt because per brush 1 volt, that is why it is written 1 into 2, look at the cursor, 1 into 2 volt, right. So, that means 230 minus 40 into 0.1 minus 2. So, now we also know that EB is equal to 224 volt and we also know EB is equal to phi Z n by 60 into P by A. So, it will be phi is 0.05 Weber, Z is 410, n by 60, P is lap connection. So, A is equal to P. So, 6 by 6 is equal to 224. Therefore, n is equal to 655.6 rpm, right. So, this is the answer. So, these problems are very simple problem, only you have to keep little bit in your mind. With this course, I mean whatever little bit we discuss, this course will be is completed, right. So, particularly at the first year level, the single phase transformer has been covered, right, and induction machine and DC motor just I have touched, not gone through the details, considering that you may be in the first years, right, or anybody can take this course, but it is just basic thing we have discussed, right, nothing is in detail. And induction machine also, because most of the time we have spent for deriving the equivalent circuit, right, but starting of induction machine or starting of DC machine we have not touched, or many other things we have not touched, thinking that you are just learning this. So, just those who will be listening this last lecture, right. So, my suggestion is practice few problems. I mean, take any book, I mean you can take any good book and you just try, right. With this, thank you very much.